You wait for coffee, so I will be very short, and I suggest that if you have any question, we'll discuss it around the coffee just next my presentation. Oh, c'est parti tout seul. So first of all, I want to thank Didier who has invited me to give this talk, even if I feel... oh, wow. The effect surprise is down now. Okay, so. Even if I feel a little bit uncomfortable because my presentation is much less impressive and technical than the others today. So I will do my best. So my presentation is about a project that we've done for 10 years. Nearly 10 years, we started in 2008 near Valence. This project is involving 4 schools around Valence and Romans-sur-Isère, which is 100 kilometers from here. And this project is about going nearly space, and the picture on the bottom right is one of those we have brought back with this project. So. Even if we don't need roads to go there, it's not about a DeLorean, but simply a box that we send into the stratosphere. This box is the one that has flight last year. And this box is attached to a latex balloon that is inflated with helium. And so in 2 hours, this balloon reaches 30,000 meters high and then burst. It's at the middle point of the stratosphere, and then just land 1 hour later smoothly under a parachute. And it can be at a range of 200 kilometers away. During this flight, the weather condition is not very friendly because the temperature can be very low and the pressure also, and speed and acceleration can vary a lot also. So a few words about the team. It's a pedagogical purpose project that involves 4 schools and 4 groups of students of various ages. The first group is at middle school, and it's about 16 years old pupils, and they are in charge in this project of choosing the physical parameters that they want to measure. For example, temperature, pressure, humidity, luminosity, and so on. And after that, they are also in charge of calibrating the sensors that are given to them. It means finding the relationship between output voltage of the sensor and temperature, for example. And after that, after the flight, they perform an analysis of the measurement. This work is done during the physics courses. The second group of students is also at middle school, a little bit younger, and they work during the mechanical engineering course. And they are responsible for designing and building the box that embeds all the stuff. This means choosing the material and choosing how to assemble them with regard to a strict set of constraints, particularly the weight and the physical and thermal resistance of the box. The third and fourth group are made of high school students who study electronical engineering or computer science, and they are responsible for the first group to the building of the sensors and the power supply management, and for the second group where several hackers from a hackerspace located in Valence is also involved in. Is responsible of embedded system and ground software management. And this project would not be possible without the help of Planet Science, which is an association that promotes science to youth. This association is funded by the French Space Agency, and Planet Science brings us a lot of stuff, hardware and technical and human help also. particularly the radio emitters that is embedded in the box, that is a long-range emitter that use frequency modulation. So a little detail about the hardware that is embedded in this box. We use of the shelf components, and the system is built around an Arduino Mega, in which is plugged a custom shield that is realized by the high school students. And in this shield, you can find internal sensors, a real-time clock, an SD card for data logging, and to this shield are connected external sensors boards for luminosity, external temperature, and also a GPS to be able to locate and track online the flight of the balloon. All this stuff is powered by two LiPo batteries, and also we embed a set of cameras that are managed autonomously, and self-powered, that are not really part of the system. A few words about the embedded software. It's very classical. On top of the Arduino runtime, we use third-party libraries, such as the ones to manage SD card or real-time clock. And we have also developed custom libraries to manage GPS, sensors, and to perform audio frequency shift keying modulation to be able to transmit data. And on top of that, we have a classical main loop which performs three things: acquire data, store data, transmit data. All this software, all the software that has been developed during this project is available on GitHub. And for the development of this software, we have been using Eclipse, and particularly the AVR plugin. Inside the Arduino, we perform a software 2 tones audio frequency shift keying modulation by bit banging, and there is a little hardware filter just in front of the emitter to clean a little bit the signal before sending it. As a requirement, we wanted to have human-readable raw messages to enable everyone who have a simple FM receiver and a PC to be able to at least see where is the object by seeing clearly the GPS location. For that, we use simple comma-separated value ASCII messages, just modulated and sent over radio. And also, we output raw NMEA frames so that the coupled receiver and decoding software can act as a virtual GPS and be connected directly to Google Earth, for example, to spot the position of the balloon. The ground station is made of two different applications. The ground station just starts with a FM receiver that you can buy for 40 euros. And behind this receiver, you can demodulate the signals that are coming from the balloon using some hardware devices, or using a hardware-defined radio chain, or using a PC sound card and some appropriate libraries. The frames that come from the balloon are also just relayed through a serial output as ASCII, comma-separated value, and handled by an application that decodes data, locally stores data, and exports the data that is embedded in frames to a JSON file, which is handled by a static website that are made of mainly three scripts. One that exports map to see the flight online, one that exports data as array, and one that draw charts. And so finally, it's an Eclipse IoT application or rather web of things applications that use a website as a flight tracking application. And we set as a requirement the offline mode to be able to transfer the whole data and the whole website, and that it can be browsed offline by anyone after the flight. So that's the end of my presentation. Here is some pictures that have been taken from flight, not last year, but before. And next flight is coming in 2 weeks, and so it will be available online. And all the code that has been developed during this project is available on GitHub if you want to have a glance at it. Thank you.